Hello, I'm William Gustafson, and in this talk I'll be introducing a poset structure on lattice minors. We'll start by looking at vertex labeled graphs. So I have a graph here on the left and on the right, the result of deleting and contracting some edges. And we'll consider minors of a vertex labeled graph to be themselves vertex labeled. Deleting an edge doesn't change the labeling, and contracting an edge merges the labels of the two vertices. So in this example, when we contract the edge between 1 and 5 and between 3 and 5, the new vertex is labeled 1, 3, and 5. As a natural poset structure on the simple vertex labeled minors of any graph, here's the poset structure for the 3-cycle graph. Here the order relation means it's a minor of, or in other words, we go down in the poset by doing deletions or contractions, and then identifying any double edges and removing any loops. One place these minor posets of graphs show up naturally is as lower intervals in the uncrossing poset. Here's the uncrossing poset of 4 to 3. It's poset on all pairings of 6 points, and the order relations correspond to resolving crossings in these medial diagrams here. And you'll notice this poset is isomorphic to the minor poset of the 3-cycle graph on the last slide. And the uncrossing poset first arose as the face poset of a stratification of a certain space of planar electrical networks. And from this theory, there's a construction to associate to any medial diagram a planar graph. And resolving crossings in the medial diagram corresponds to deleting or contracting edges in this planar graph. I have 2 examples of this construction here. The details aren't really important for this talk, but what is important is that whenever this associated graph has all of its vertices on the boundaries of the disks, such as in these 2 examples, then the poset of simple vertex labeled minors of the graph is isomorphic to the lower interval in the uncrossing poset up to this pairing. The kinds of graphs that you can get from this construction are all wedge products of graphs that can be embedded into the disk. Okay, so then our observation here is that if we have a wedge product of any graphs that it can be embedded into the disk with all of their vertices on the circle, then the poset of simple vertex labeled minors of this wedge product is isomorphic to some lower interval in an uncrossing poset. Patricia Hirsch and Richard Kenyon showed that the uncrossing poset is isomorphic to the face poset of a regular CW complex. So these special wedge products I just mentioned have minor posets that are isomorphic to the face poset of a regular CW sphere. And it's a natural question to ask whether this result holds for any other graphs. And one might also ask whether this could be generalized beyond graphs, say to matroids somehow. Alright, and then we'll see in this talk that indeed the minor poset of any graph is isomorphic to the face poset of a regular CW sphere. And to prove this, I use a construction which will necessitate generalizing this beyond graphs to the level of polymatroids. In order to generalize the notion of simple vertex labeled minors of a graph to polymatroids, we use the lattice of flats of a graph. So here in the top left is a graph. Next to it is its lattice of flats. This is the lattice of all the partitions of the vertices whose blocks are the connected components of a subgraph. And then to the right, we have the result of contracting the edge between 1 and 2, and then identifying the 2 parallel edges. The lattice of flats of that graph can be obtained from the original lattice by taking the upper interval from the atom 1, 2/3/4. Right, this is the partition corresponding to the edge we contracted. Then on the bottom left is the result of deleting the edge between 3 and 4, and its lattice of flats can be obtained from the original lattice by removing the partition 1/2/3/4 and only keeping those partitions that are a join of some of the remaining 3 atoms. So our contraction operation on the lattice of flats means to take an upper interval, and the deletion operation means remove an atom and only keep joins of the remaining atoms. And our theorem here says that simple vertex label minors of a graph are in bijection with the minors of the lattice of flats. So this is how we'll generalize the notions of deletion and contraction. We can generalize the contraction and deletion operations just mentioned from lattices of flats of graphs to all lattices, but in hindsight we find we want to keep track of a notion of a generating set. So to do that, our basic object will be a generator-enriched lattice. This is a pair consisting of a lattice L and a subset G that doesn't contain the minimum and generates the lattice under the join operation. Necessarily, since G actually generates L, it has to contain all the joint irreducibles, but we're allowing it to be larger as well. I just want to mention real quick that a generator-enriched lattice encodes the closure operator of a polymatroid, but for time I won't go into the details. On the right here, I have a few generator-enriched lattices depicted. To depict a generator-enriched lattice, we add some edges to the Poset diagram whenever we can go from one element to another by joining with a generator. So on the top is the rank 3 Boolean algebra, as well as the lattice of flats of the 3-cycle graph, and each of these are generated by the 3 atoms. In this case, we just get the Poset diagram, and this is because these lattices are geometric. Then on the bottom left, this pentagon lattice will be a recurring example. Its generators are A, B, and C. And on the bottom right is the rank 2 Boolean algebra with the top element considered a generator. We'll also need the notion of a strong map between generator-enriched lattices. This is a generalization of strong maps between matroids, but it is a join-preserving map between the underlying lattices that sends each generator either to a generator or the minimum. We say strong map is surjective if every generator of the codomain is hit by a generator from the domain. Now we can define the deletion and contraction operations for generator-enriched lattices. This is a straightforward generalization of the same operations for lattices of flats of graphs. We index both these operations by subsets of the generating set. And then the deletion by I has as generating set G minus I and has minimum 0 hat, the same minimum as L. The underlying lattice here is just all joins of elements from G minus I. The contraction has as generating set all the old generators joined with all the elements we contract. The minimum of the contraction is the join of all the elements we contract. And here the underlying lattice will be an upper interval from that minimal element. I have 2 small examples here. On the bottom left is a face lattice of a square generated by its 4 atoms. And in the middle is the deletion by the first atom. You'll notice we also lose the 2 elements just above that atom because they're not joins of the remaining 3 atoms. Then on the right is the contraction by the same atom. And notice here the top element is a generator that's coming from the 4th atom on the right. Now we come to the poset structure mentioned in the talk title. This is what I call the minor poset of a generator-enriched lattice. It consists of all minors ordered by the relation is a minor of, or in other words, you go down by taking deletions and contractions. And it's also joined with an artificial minimum denoted empty set. Here's a small example, the minor poset of the rank 2 Boolean algebra. You'll see in this case it's isomorphic to the face lattice of the square. This continues in general. The minor poset of the rank n Boolean algebra is isomorphic to the face lattice of the n-dimensional cube. This is because Minors of the Boolean algebra are simply the intervals of the Boolean algebra, and as is well known, the lattice of intervals of the Boolean algebra is isomorphic to the face lattice of a cube. Here are two larger examples. On the left, we have the lattice of flats of the three-cycle graph. And you'll notice this minor poset is isomorphic to the poset we saw at the beginning of the talk of simple vertex labeled minors of that graph. On the right is the pentagon lattice. And just a few quick facts I'll point out. This poset is ranked by 1 plus the number of generators. So at rank 1, all those 1-point lattices have 0 generators, and just about that 1 generator, and 2 and 3 at the top. And the atoms in this poset correspond to the elements of the lattice, and the rank 2 elements correspond to the edges of the diagram. My main theorem for minor posets is this construction using a zipping operation due to Nathan reading. So this theorem here says that a strong surjection between generator-enriched lattices induces a sequence of zipping operations between the minor posets. And I have here some figures as an example showing you how this construction usually plays out. So we start at the top left here with the rank 3 Boolean algebra. And the red labels are indicating the strong surjection. We're mapping onto the pentagon lattice down here. And just next to the Boolean algebra is the cube as a cell complex. Recall the face lattice of the cube is the minor poset of the Boolean algebra. In order to make this construction easier, we first factor the strong surjection so that at each step we only identify 2 elements. And in the first step we identify 1, 3, 1, 2 to get to this lattice in the middle. And on the complex we zip the corresponding edge. And that means we contract that edge and identify the 2 vertices. Then in the next step, identify the 2 elements along the top red edge in the lattice. And again on the complex we zip the corresponding edge. And now this time the triangle wrapping around to the back on the right has turned into a 2-gon. So we zip that 2-gon as well, contracting it and identifying the 2 edges. Then in the final step we identify the last red edge and zip the corresponding edge on the complex again. Once again we make a 2-gon, which we also zip, and then we end with this complex down here, whose face poset is isomorphic to the minor poset of that pentagon lattice. And in general, the way this construction plays out is whenever we identify 2 elements on the lattice, we first zip the edge on the complex, and then go up in dimension and zip any cells whose boundary is made up of 2 closed cells. We just saw in that example that the minor poset of the pentagon lattice is isomorphic to the face poset of a regular CW sphere, and this is a corollary of this zipping construction. The minor poset of any generator-enriched lattice is isomorphic to the face poset of a regular CW sphere, except for a trivial case of when your lattice has only 1 element. That's all I have to share. Thank you so much for listening.